And we're back. Welcome back and happy Tuesday. Today, we will turn our focus to an interesting example to get you started in looking at computational issues and trade-offs pertaining to correspondence. Now, this is purposed with giving you a little bit of a flavor of both what the Matlab code looks like, as well as some practical, dare I say, engineering practicalities or issues concerning computer vision types of applications. But before we begin, some administrative bits. Project number 2 will be due today, Tuesday, at the usual 11:59 and 59 seconds. That's 1 second before midnight. So why don't we begin? Where we last left off, we talked about a few modules ago RGB color space, and we said a color is represented as a coordinate in this space, and that coordinate represents the amount of intensity in a mixture comprised of primary colors red, green, and blue, hence the name RGB in this color space title. And so we also most recently talked about a grayscale image, and we looked at the so-called intensity surface, a kind of relief map, and that relief map defined the content of an image. We then measured or characterized the shape of this intensity surface using the derivative, the partial, with respect to x and with respect to y. And there's a typo there, with respect to x and with respect to y in image coordinates. And we said we're trying to characterize, so here's my dy, we're trying to characterize the flat parts, the hilly parts, as well as the bumpy parts of the intensity surface. So we took our definition for the derivative. No, that's correct. So we took our definition of the derivative and we looked at it from the perspective of the intensity surface, and we came up with an expression, a discrete approximation of the derivative definition, and we reduced that down to a set of coefficients convolved or multiplied by, used in a weighted sum for locations in the image surface, intensity surface, in image coordinates. And so we used this information to populate a mask, a so-called convolution mask. And when we place this mask, center it over position xy in the intensity surface, and compute the weighted sum for those positions under the mask on the intensity surface, we get that discrete approximation for the intensity surface. And so we slide this mask and do that for every pixel xy in intensity surface in image coordinates, and we get the so-called edge map. And by extracting or identifying the top p% edges or steepest local slopes in the intensity surface, this gives us the strongest edges in the image that we can use to describe content in the image. And we saw an example of that in Matlab. So let's take a look at the correspondence problem again. We said in correspondence, we make the assumption either we have a camera that's moving or we have two cameras, and we get two images, one at time t0 and one at time t1. Now, in this case, if we were moving the camera to the right, everything in the image plane of the camera goes whooshing to the left. And so we enterprise to see where in this image at time t0 this red cropped region has gone at time t1. Now, of course, a priori, we don't know where it went, so we have to search for it. So I take an image, I move the camera, then I take another image, time t1, and the question then is, where did the doorway go, this red or pink region, go from time t0 to t1? Now, of course, there are a lot of potential locations, but you have to search for it. It could have been up here, it could have been over there, it could have been down here, it could have been this one. But you have to search for it. Now, of course, that's easier said than done because there are a lot of practical engineering issues wrapped up in this needing to search for it. So we need some function, and that function is going to be a measure of similarity in the appearance in the image between at times T0 and time T1. More correctly, we have a patch, we'll call that F, and that's the query, what we're looking for. And then we have a number of candidate locations or patches in the image at time T1. And so I list out down below G, that set of candidate patch locations in the image at time T1. And so that function we need, one of which we can use, we've already learned, namely correlation. And so literally we're looking at the correlation in the intensity values associated with that pink region, and we're measuring correlation with respect to the intensity values from each one of these green cropped regions. And so this is a little bit of a refresher, which we have from last semester. The expectation is just the probabilistic weighted sum. So I goes from 1 to n for n many examples, the ith example times its probability. Now, of course, if we're dealing with discrete data samples, you can make the assumption, simplifying assumption, that each one of them are equiprobable. So the probability p of x, I, would be 1 upon n, and we get the sample mean. The variance is the probabilistic weighted sum of each of the measurements x, or random variable x, minus its expectation quantity squared. And we squared it because we don't care about the direction if it's smaller or greater than its expectation. We care about the magnitude. And so we have our sum, x minus mu, quantity squared, times p of x. And the standard deviation, we said sigma is the square root of the variance. All right. We also talked about covariance. And covariance was the product of the difference between two different variables, x and y, and their centers or their mean. And so that's the expected value of the product between x minus its mean, e of x, and y minus its mean, e of y. Now you notice there's no square term here, so if one of them is positive and the other is negative, you're going to have a negative covariance. And so this is the double summation, iterating over all values of x and y, of x minus mu with respect to x, y minus mu with respect to y, times the joint probability p of x, y. Now, we had depicted some charts last semester that talked about examples of a so-called positive correlation. That's this chart on the left-hand side. And we talked about negative correlation or covariance. That's this chart on the right-hand side. And so this covariance talks about a unit step increase of one measurement or value with respect to one axis for each unit step increase of another. And so here in this chart, we have economic growth versus stock market return. And you can see for these points, if you go from one point to the next, for some delta unit step increase in economic growth, we have a commensurate delta or unit step increase in stock market return. And because it's a positive increase, the coupling or the relationship between these two variables, economic growth and stock market return, is a positive one, and hence we say a positive covariance. They vary together, co-vary. Likewise, on the right-hand side, we have another graph, and that is world oil production, with gas prices as a function of world oil production, or world oil production versus gas prices. And we see the opposite direction for covariance, a negative covariance. If world oil production increases, some unit step increase, we see that the amount of gas price goes down, some unit step decrease. So that's a negative covariance. They vary together negatively. An increase in one results in a decrease in the other. And so if we look at these points and we were to do a kind of straight line fit, for the positive covariance, we get a positive sloping line, sloping upward. For a negative covariance, we get a negative sloping line, sloping downward. So if we take our covariance and we normalize it by dividing it by the product of two things, the standard deviation of variable x and variable y, we get correlation. And correlation normalizes it to a range of interval from -1 to +1, where -1 is perfect negative correlation. Unit step increase in one is the same unit step increase in one is the same magnitude step decrease in the other, and a +1 correlation, which is a unit step increase in one, is the same unit step increase in the other variable. Okay, so that's a little bit of a refresher from last semester. And so now, as we said, going back to using correlation for the correspondence problem, the correspondence then is the patch of the intensity surface that maximizes this correlation. And so we're going to measure correlation. So there's our correlation, rho, for each one of these patches, G1, G2, G3, G4, and all the patch candidates in the image at time t1. We're going to run this correlation between our pink cropped region, we call that our query, and each of these target proposed regions, G1, G2, G3, and G4. And of course, the correspondence is the one that is the GI, that patch and the target at time t1 that maximizes the correlation. And so you select your query, okay, and that's our patch at time t0 that we wanted to know where it went at time t1. And then we initialize a search. And so we start our search, and let's say we initialize our search in this upper left-hand corner of the image at time t1, and then we measure correlation between the two, and we get some value. So then we maintain our query, so we're going to keep this pink cropped region, and we're going to update our search. So you notice here now we move this crop box to crop a different region of the image at time t1. So we update our search, and then we crop it out. We have a new target or potential target in the image at time t1. And then we compute our correlation again, get another value. And we compare this new value to the old value, and then we do it again and again and again, iterating in a loop for all of the possible target locations in the image at time t1. So we start out, we initialize our query, and in a loop, we crop, we compare using correlation. We save that match score, the correlation score, and then we update the crop region by shifting it along some schedule. Now, of course, this seems all fine and good, but there's a little bit of a practical problem in this. There's a trade-off between resolution, the level of granularity for which you're searching, and the performance. And so let's imagine we tessellated the intensity surface so that the target regions in the image at time t1 do not overlap with one another. Well, at time first iteration for that loop, we're going to search the first crop region, then shift and search the next crop region. Now that's going to make this search much faster, but it lessens our ability to find more precisely where that patch at t0 went within the image at time t1. That's more coarse resolution. So it's faster, but localization, the finding of that new location in the image at time t1 is not as precise. And so this non-overlapping tessellation is fast, but it gives us low resolution search. Okay, we can also have overlapping target regions in the image at time t1. So let's now imagine instead of tessellating, non-overlapping, we're going to shift our target region, that search, that crop region in the image at time t1. We're going to shift it some small number of pixels, and each location from one round to the next in our loop where we're searching is going to overlap with the other. And so you can imagine then we start our crop region in one location, upper left-hand corner, and then we shift it 1, 2, just a couple little pixels a little bit to the right. And you'll notice here that the crop region for the second position shares the majority of its pixels with the crop region for the first location. And so we do that again and again and again, each time running our correlation score, saving the match score, looking in all parts of the image, overlapping, shifting to the right, as well as shifting down. As we get to the edge, we come back around to the next left-hand side of the image and shift down. And we keep doing that to search all possible target locations that we can have in the image version at time t1. And so we can do this, and the good news is that it's very high resolution. Because we're only moving this crop window in the image at time t1, only one, at the minimum, pixel at a time, it's very high resolution. It will precisely, in this case, locate where that crop region at time t0 went in the image at time t1. But the bad news is it's much, much slower because there are many more locations to search, to visit, and evaluate. And so there's this dichotomy. On the one hand, you want it to be fast, but what you pay for is the loss in level of granularity. Your ability is lessened to be able to find precisely where it went in the image at time t1, versus high resolution. You can find precisely where it went in the image at time t1, but it's a lot slower. You don't get your answer nearly as fast. And so there's also a kind of happy medium, and it's based on a little bit of physics. And there's this notion of constancy, right? Inertia, that when you move, your new location is someplace near your old location plus or minus some delta. Items don't move arbitrarily from one location to the next far away instantaneously. They have to visit locations nearby in between their position in one location and a position in another. And so instead of searching every single region, you can search just that window within the image where you believe that object has moved when it started at time t0. And so here on the left-hand side, we have a coordinate system on the image at time t0, and we note where the center of the bounding box is for our query. And so if we know how fast the camera is moving, well, we know velocity is distance per unit time, and distance is velocity times time. So knowing how fast the camera moved, you say, okay, well, if I know it was moving at a certain rate, I know regardless of the direction in which it moved, that red query region in the image at time t0 couldn't have moved plus or minus some delta in the x direction and in the y direction. And so we then take that same x direction and y direction in the image at time t1, the same coordinate where that crop region started in the image at time t0, and we take the measurement of that image, that query, and we go plus or minus some delta in the x direction and the y direction. And then we limit our search for targets in the image at time t1. We limit it to that bounding box, which consists of the original location at time t0 plus and minus some delta in the x direction, plus and minus some delta in the y direction. And so what this does is constrains that particular region of the intensity surface area where we're going to do our search. And so this allows us to have fast search because we're searching fewer locations, but also high resolution search because we're searching by shifting one pixel at a time. Now, of course, this isn't a magic solution, because if that velocity is very large, of course, that bounding box is going to be very, very large and degenerates into searching the entire window. Okay, so let's try this out in Matlab. We're going to implement this initialization of the query and iterating in a loop, the cropping, extraction of a patch image, comparison, the correlation, saving the match score, and the updating. And so one of the things I want to highlight is the impact of the degree of tessellation, this difference between how far these target windows, crop regions in the image at time t1, how far apart they're spaced, and that trade-off between runtime and level of granularity. Okay, so let's go into Matlab. I will meet you in Matlab. So we're here in Matlab, and we're going to demonstrate searching using a query, and that query has been pre-cropped out of a larger image. So you can imagine we have the query region from the image at time t0, and then we have the image at time t1, and we're going to search for that query image. So we define our query image, which is called Oprah head, and then we define the target image, Oprah in a crowd. Okay, and so we start out and we read in the images, and we measure their size, the number of rows and columns, and then this X shift and Y shift is going to be the amount where this target search in the image at time t1, the amount by which it shifts from one round of the loop to the next. And so in this case, it's going to shift 10 pixels at a time. Let's change it to 20 pixels at a time for a very dramatic shift, just to illustrate how quickly this algorithm will run if it doesn't have to search as many locations. And so we have a vector describing the crop, and it's the XY location, upper left-hand corner of the crop window, and we define the width and the height, so it's just the data structure. We start out with some variables to store the correlation score as a basis or starting place of our search, and then we loop through our image, shifting some number at a time of pixels along X and along Y, defined by X shift and Y shift. Now, in this particular example, we don't shift all the way off the edge of the image. We make sure that the right-hand side of the image and the bottom of the image don't shift off the edge on the right and don't shift off the bottom of the image. So then we do a crop, and that's IMCrop. It's a Matlab API routine, and we get back the cropped image region. We convert them both to grayscale, the query image and the cropped image, and then show you some statistics. Look at the cropped image, look at its histogram, and this continuous histogram plots the RGB color channel distributions on the same graph, and then show you the cropped image. So then after that, I draw the crop window, pointing out or demonstrating or drawing, showing you where it's getting its crop information for each one of those targets that it's evaluating using correlation. So then I do my correlation match, which is just computing a correlation, and then I hang on to the maximum correlation score in addition to the X and Y coordinate for that target crop window in the target image where it achieved that maximum score. And then I display the image and I redraw that crop region in the original image. All right, so let's run this, and I'm going to start out, set a breakpoint, and then I'll clear the breakpoint to show you what's going on. So why don't I go ahead and just run. Okay, so let's continue. And with that, I'm going to put these windows separately. Let me resize them a little bit, and it updates. And you'll notice here in the image on the left, I am searching. You see that red crop window changes position, shifting 20 pixels to the right and 20 pixels down. And then on the right-hand side, there is the query. That's Oprah's head. And on the right-hand side also, you see the current version of the target for the crop window. Now you notice that the histogram for red, green, and blue is adjusting. It's showing you what the color distribution is, the amount of red, green, and blue in RGB color space representation for that particular target under consideration. And so here you see the histogram for the query, and then the histogram that's for the target region in the target image that's under consideration at the current moment. And so it goes relatively quickly, and you'll see it move and slide and move and slide. And eventually it will look at all of the pixels in the image, matching up or lining up the crop window, and it will just halt. And then you'll notice at the end of it all, when this completes, it will draw the target window where it got the maximum correlation. And so one of the things you'll notice then is if you decrease X shift and Y shift, you'll notice that it gets closer and closer and closer, ground truth, to where Oprah's head is in the image. But as you increase the X shift and Y shift, it gets further and further away, but it runs much more quickly. Okay, so let's pause this and let me clear the breakpoint. Let me quit this, and let's change this X shift and Y shift to be something much bigger, much, much bigger. Let's say 60 and 60. All right, so we try this, and let's just rerun it, and you can actually see that it goes much, much faster. And in the interest of time, just want to make it really, really fast, just to show you that when this program runs to completion, that it draws the best match within this target image. And so not too much longer. It should finish now. Okay, and so that's what it thinks Oprah is, and it's clearly not Oprah. But if we were to decrease the size of X shift and Y shift, it would exactly, precisely identify Oprah. Now, I'm not going to run that because it would take longer time than I have, but certainly I've posted this on the Blackboard, and please download this and tinker with it for yourself. Okay, so with that, let's go back to PowerPoint. I will meet you in PowerPoint. So we're back in PowerPoint, and that's just a demonstration of a practical trade-off, and also when you're implementing a lot of these computer vision types of analytical programs, that you really have to pay attention to the algorithmic complexity. And there are many trade-offs in general between specificity, how high level or low level the resolution is for locating the particular region in the image at time t1 where this query patch went, and the runtime. And so it's one of these trade-offs between resolution, level of granularity, and runtime. And striking the right balance is all the difference between success and failure for your program. All right. So with that, that's all I had. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.